While the trail's still hot, that's when the fire investigation begins. The investigation into key elements, such as the cause and the origin of the fire. Elements which are important because they can help determine coverage and liability. When the trail gets cold, it's too late. Valuable information can go up in smoke. Legal, criminal, and insurance investigations all begin with good information. In this video, we're going to take a closer look at just how that information can be gathered. We'll look at what to do at the fire scene, what to do after the fire, and how to determine the fire's cause. We'll also be taking a closer look at the fires caused by liquid accelerants and how those fires behave. The investigation begins as the fire goes out. Looking for hidden flames or sparks, the overhaul, is a priority. But the scene doesn't have to be destroyed to do the job. The remains of the fire contain valuable information, so don't demolish or discard possible evidence before records have been made. You also need to talk with everyone involved. This may include the owner of the property, anyone who lives there, the first firefighter on the scene, the police, anyone who is just standing by.
The dog started barking. I looked out, and there was a guy running through the yard between the houses here.
Okay.
And
did you see anything? And what did you see when you arrived at the scene?
And it was starting to come out the side of the road.
Okay, so you're basically saying that you saw the same thing.
Yeah,
Ask them questions about what they saw, getting as many details as possible, and be sure to get names and phone numbers.
Okay, did you see anything suspicious like anybody?
There's a lot of questions you've got to ask, like how the alarm came in, what structure we had. Were there any bystanders or witnesses out there? What was the color of smoke, the color of flame? Sometimes the situation may be too big for you to handle alone, like with a death or an injury. Or say, for example, the structure burns completely down. And of course, anytime you may suspect arson or anything else that's unusual, that's when you've got to call in that trained investigator.
When the fire is out, the record making, including drawings and photographs, should begin. This is one of the most important things you can do to preserve possible evidence. Sometimes a sketch shows a detail a photo doesn't catch, while a photo can show a detail that you didn't notice while making the drawing. You need to sketch the entire scene and take photos inside and outside. Pictures should be straightforward, so they're as accurate as possible, and should include anyone who is hurt, any suspected causes, and where you think the fire began. It's important to make a careful examination of the entire scene. Look under the eaves, around the doors and windows, around the vents. Check to see if the utilities, particularly gas and electric, have been turned off. If they have, an accidental fire is less likely. And check for anything unusual, like footprints, burn patterns, containers, anything that just doesn't seem quite right. When checking out the interior, start at the place where the smoke, heat, and fire seems lightest, and go towards heavier concentrations.
You know, it's important to look at the way things burn in relationship to what's in the room. Keep in mind, all things are not always as they seem. Take, for example, this couch over here. We've got a lot of surface burning coming up on here, a lot of radiant heat all the way across through here. Had some newspapers that was here during the fire. Radiant heat down low. Material kind of crunching down. Let's look over here at this couch, for example. A lot of low burning here. We've got the cushions that are basically burned out all the way up through. Burning coming across here. A lot of high burning coming up through here. Telling us this couch had a lot more damage than the last couch. You know, glass is another way that we can look at this. Crazing of glass is basically the way it breaks up when heat's applied to it. Small crazing of glass tells us that we're closer to the point of origin. Larger crazing of glass, on the other hand, tells us we're more farther away, more remote from the point of origin. Another situation you might encounter could be a light bulb. This particular situation, we've had heat applied to the light bulb, starting to weaken the glass. The gas inside starts pushing out because of the difference in pressures, and starts pushing it toward the most heat, the point of origin. One thing that you've got to keep in mind, get everything you can while you're there. Don't think, well, I'll come back later and pick it up. Get it now, because you may not have that second chance.
Usually, there is about 3 feet of ceiling damage for every foot on the floor. The greatest ceiling damage will be above and indicate the point of origin. Determining the point of origin where the fire began is an important responsibility. The point of origin provides much valuable information about the fire.
As you can see, the fire originated down here in the couch. It started burning up and up, burnt the picture, carried on up, and eventually spread out, forming a V. Normal fire growth is upward and outward. We basically have 3 types of V patterns: vertical, horizontal, or combination. And there's several things that can affect the V: the wind, drafts, structural elements, or even the fire department ventilation.
In many situations, major help in pinpointing the area of origin can come from a canine accelerant detecting dog. Here, this dog found the place where liquid accelerant had been poured more than 24 hours after the fire had been extinguished. Many states as well as private companies are making these dogs available today. Collecting the evidence and looking for the point of origin help us in reconstructing the fire. It helps us to confirm the spread and verify the path the fire traveled, as well as whether flashover occurred. All of this is part of determining what started the fire.
So what does it take to start a fire? It takes just 3 things: heat, fuel, and oxygen. When these are combined in sufficient quantities, a fire is going to occur. Oxygen is present in everyday situations. Fuel is present in the form of combustibles, such as a couch, a chair, or sofa. It's the job of that fire investigator to determine how the heat was introduced and why.
Knowing how the heat was introduced will help determine how the origin of the fire is classified. A fire can be caused by an accident, an act of providence, or an intentional incendiary setting of the fire. A key job of the fire investigator is to determine whether an incendiary fire, also known as arson, has occurred. Accidental fires are caused by people or malfunctioning systems. Systems such as faulty heating or cooking equipment, electrical malfunctions, smoking, burning trash, open flames and sparks, gas or dust explosions, fireworks, low-temperature ignitions, and spontaneous heating. Providential fires, on the other hand, are caused by nature, usually lightning. So if we're going to say that a fire was providential, we want to make sure that the weather or other conditions are consistent with that conclusion.
What a fire investigation is about is looking for the truth, and that may include arson. Anything strange, unusual, out of the ordinary you want to note. These are red flags. These red flags may be evidence of arson.
These include multiple fires, suspicious trailers, newspaper ashes, the presence of flammable and combustible liquids, or an absence of other accidental fires. There might be other crimes involved, such as burglary, or the fire might have spread in an unnatural pattern. You should look for excessive damage, or a site which is somehow blocked from ready view. And you should also consider the timing. If the fire occurs conveniently during a weekend or holiday, or during an electrical storm, something may not be right. Finally, consider the possibility of a juvenile fire setter. In some communities, 40% of all fires are juvenile-related. Recent FBI statistics show that 47% of the individuals arrested for arson were under the age of 18. These juvenile fire setters fall into 4 distinct groups: the curious, ages 3 to 7, the experimental, ages 5 to 10, the deliberate, ages 8 to 18, and the malicious, also ages 8 to 18. In all communities, this is a problem that needs attention. One of the most common methods of setting fires is through adding fuel, specifically flammable and combustible liquids known as liquid accelerants. Most fires are predictable. If you set a fire in the fireplace, the conditions present at the time dictate how the fire will burn. But the fires that have been set using accelerants follow different rules. Because they do, they leave clues. For one thing, some of them, such as gasoline, fuel oil, kerosene, and mineral spirits, have an odor. You may be able to find a trace of the smell. Then, the color of the flames or smoke may provide information. Flames that are red or orange might be suspicious, especially if they're at floor level or other areas that aren't particularly combustible, while the smoke from a liquid accelerant fire is intense and black in the earlier stages of the blaze. Since most liquid accelerants are lighter than water, we say they have a higher specific gravity. This means they'll float to the top of wet surfaces and standing water. The water used in fire suppression may, in fact, float unburned liquid accelerants to the surface. To spot them, look for the telltale rainbow effect. Another indication that liquid accelerants may be present is speed. Liquid accelerants live up to their name. They make a fire burn faster than an accidental fire, like this charcoal lighter fluid, which helped the fire spread up to the bed. Lack of lateral spread may be an indication of an accelerated fire. Usually fires progress laterally. But since liquid accelerants burn hotter than most household items, they'll generally cause the temperatures at the ceiling to increase faster than in a normal fire. This intense heat at the ceiling level can accelerate the venting process and cause the fire to burn up rather than out. Normal fire behavior is gradually up and over. If the accelerants are poured in a concentrated area, the fire may quickly ventilate and cause distinct vertical destruction. Usually, the pattern narrows at the ceiling, leaving an inverted V pattern. Here, the accelerated fire went up the side of the house very quickly, while the rest of the house is hardly affected. Vapor density is a means by which gases or vapors are classified by comparing them to air. Lighter vapors will rise to the ceiling, while heavier vapors will sink to the floor. It's easy to think of vapors as lighter than air, but this isn't always so. In fact, the vapor density of most flammable vapors are heavier than air, meaning the vapors will sink to the lowest level possible. These heavy vapors are very volatile, as we'll see in this experiment. The vapor density of propane gas is heavier than air. Here, when propane is blown into this channel, it sinks to the bottom where it is ignited by the candle. Now, gasoline vapors placed at the top of the channel vaporize and travel to the bottom, where they're set on fire. Notice, it's not the liquid that burns, it's the vapors. So how does vapor density affect a house fire? When gasoline is poured on a floor, the vapors remain at floor level, mixing with the air and spreading over the entire room, not just the spots where the gasoline was poured. When the vapors are ignited, very rapid combustion occurs. Just as water fills a container, vapors fill a room. Watching it in slow motion, this filling action is apparent. The gasoline ignites if it reaches what's called a flash point. The flash point is the lowest temperature at which sufficient vapors are given off to ignite or flash across the surface when exposed to an ignition source. The flash point of gasoline is minus 45 degrees Fahrenheit. So when gasoline vapors are warmer than minus 45 degrees, which is usually the case, they can be ignited. In this experiment, the gasoline in the bowl is chilled with dry ice to a temperature below minus 45 degrees. As long as the vapors stay this cold, they won't ignite. Once the gasoline is warmed to minus 45, the vapors will light. Flash points of liquids cover a wide range of temperatures. The flash point of kerosene, for example, is quite high, between 110 and 165 degrees Fahrenheit. So the vapors of kerosene won't ignite when it's cooler than 110 degrees. Trying to ignite kerosene vapors at air temperature doesn't work. The liquid has to be heated to reach the flash point. Ethanol has a flash point of 55 degrees. Linseed oil, a substance used in refinishing furniture, has a flash point of 430 degrees. And cooking oil, which is often blamed as a cause of kitchen fires, has a flash point of 490 degrees, much, much less volatile than gasoline. The vapors of various liquids can be very explosive. All liquid accelerants have a flammability or explosive range, an amount of vapor mixed with air in a proportion that, when in contact with a spark or flame, will cause an explosion or fire. In this experiment, the combination of oxygen and acetylene is such that when the fuse burns down, a violent explosion occurs. Let's take a closer look at a burn involving a vapor explosion. The coffee maker has been specifically wired to help start the fire. Then, 4 gallons of gasoline were poured through this house 8 to 10 minutes ago. So there's been time for the vapors to mix with the air. You can see the fire burning normally at first, with no gasoline vapor involved. But when the tar paper falls into the flammability range, a vapor explosion occurs. This is like the balloon experiment in an uncontrolled situation. A vapor explosion is called a low-order explosion, and it's different than a high-order or true explosion. A vapor explosion needs oxygen to explode. A true explosion produces its own oxygen. A vapor explosion pushes outward on the walls, upward on the ceiling, and downward on the floor. Because of the rapid buildup of heated air, the pressure within the structure is much greater than the air pressure outside. The power in an explosion like this is tremendous and unusual. See the glass pulsating? It was blown 80 feet from the building. But while the glass was blown out, the objects inside the building are still inside. In this type of explosion, objects inside are rarely blown outside because the pressure buildup is equal on everything inside. The front wall separated from the floor about 6 inches. But there won't be a crater as we might expect from a true explosion, such as one involving dynamite or TNT. A vapor explosion is usually followed by an intense fire, which will burn until the accelerants are consumed. Because of this intense burning, liquid accelerant fires cause heavier damage to the lower portions of the room. The temperatures are higher near the floor because the accelerant is fueling the fire and making it burn fast and hot. In a normal fire, on the other hand, the heat at the ceiling is about 33% higher than at the floor because there's no more fuel down below. So how does this affect your investigation? For one thing, pay particular attention to floor level charring. Heavy damage near the floor will show more intense heat, possibly because liquid accelerants had been poured there. Then there are a few more clues to look for. Usually a fire will burn heaviest in the area where the accelerant was poured, as there is more fuel to feed the fire. So there may be a distinct line between the burned and unburned areas. Also, the liquid may be absorbed by the floor material itself. If the fire lasts long enough to consume all the liquid, the area will be charred. If the accelerant soaks through joists and cracks in the floor, holes will be visible through the floor, and charring will be visible on the joists or beneath the subflooring. Different types of flooring create different distinct patterns. Accelerants can also explain burning that is visible under furniture or in other areas that otherwise would be shielded from the flames. Normal fire progression is upward and outward, and the lowest structural members, such as studs and floor joists, are the last to be consumed. If you find a joist that's heavily damaged in a concentrated area or evidence of a fire that burnt downwards, liquid accelerants may have been present. There are so many clues to a fire caused by liquid accelerants, but it's never really cut and dried. For one thing, an individual fire started with accelerants may not have all these characteristics, but it will have some. And for another, some of the things we've seen can happen in an accidental fire. For example, draperies may fall down and burn the carpet or create holes in the floor. The important thing to remember is stay on the lookout for evidence of liquid accelerants or other red flags that might indicate arson, and then compare that information with the other data you've gathered in your investigation.
As you carry out your investigation, talk to as many people as you possibly can and keep track of the details. That way, when you make a determination, you're going to have as many facts as you possibly can. Facts you're going to use to help determine what really started the fire.
At the scene, after the smoke clears, and determining the cause. These are the three major stages of investigating a fire. You play a key role in gathering and validating this important information. When the fire's burning, the trail's to you to get the facts before the trail gets cold.